All right, lastly, I'd like to invite Dr. Raphael Stern, Assistant Professor of Civil, Environmental, and Geo-Engineering at the University of Minnesota, to discuss their project, Cybersecurity of CAVs via Traffic Anomaly Detection.
Thank you. Thanks a lot. And I am mindful of the fact that I'm what stands between you and a coffee break. And so I'm going to try to end on time to make sure that we can be at that coffee break. What I want to talk about today, I'm going to look at this I'm a civil engineer. I'm going to look at this sort of from the civil engineering, or really the traffic flow perspective, maybe a slightly different perspective on cybersecurity than you've seen before. So hopefully you'll see something new. So I'm coming as the third talk in a session on cybersecurity. I don't think I need to motivate this, but cybersecurity is a big problem. Anything that is connected to the internet has potential vulnerabilities. As somebody who was hacked this week and lost my credit card info, I can tell you that anything that connects to the internet has cyber vulnerabilities. For automated vehicles or connected and automated vehicles, there's a couple of different sort of common attack vectors that we can think of. One of them is, we've heard a little bit about roadside units this morning or this afternoon already. So you've got units at the side of the road that are communicating with the vehicles. Those can be compromised. Those messages could be compromised. Vehicles could act poorly or act incorrectly based on faulty information they get from there. Or if there's vehicles communicating with other vehicles, so some sort of communication-based attacks, we can imagine that those messages could be compromised as well. And finally, sensor-based attacks. So you could have sensors on the vehicles that the vehicles rely on. We've heard a little bit about those already. Imagine one of those is compromised somehow. Now the vehicle is acting on a picture of the world that is very different from what the world is actually looks like in front of it. There have been a number of sort of high-profile examples of this. You might have seen this one at the top here. Some researchers at the University of Illinois a couple of years ago had this really creative way. They said, okay, if a car is doing perception based on a neural net, it's looking at things around it. If we know how that neural net is trained, we can maliciously adjust and make really, I mean, you can imagine just a couple of stickers on that stop sign. We can maliciously adjust the infrastructure around it and get it to see a very different thing. So in this case, instead of seeing a stop sign, that car now sees a 45-mile-per-hour speed limit sign. I don't think I need to explain why that is a problem, right? These are some very sort of obvious attacks that could be pretty catastrophic. There was an example a couple of years ago. A couple researchers was featured in a Wired article, got a lot of sort of public notoriety. Were able to take a vehicle, a commercially available vehicle, through the infotainment system, get access to, so basically phone is connected to the Bluetooth is connected to the infotainment system. They compromise the phone, get into the infotainment system. The infotainment system was not air-gapped from the vehicle system. And so now they're in the vehicle system, they're on the CAN bus, and they were able to take over the steering, shut off the engine, et cetera. So these are some high-profile examples of cyber attacks or potential cyber attacks on vehicles. Like I said, I'm not really like a automotive researcher. I'm more of a traffic researcher, and so I want to think about this from a traffic flow perspective. What if something like this happens? What happens from a traffic flow perspective? I'm going to show you a slide that I love to show. At the top, we see traffic in the wild, and there's a lot of good reasons for traffic jams, but there's a couple of bad reasons for traffic jams. And one of those is what we see at the upper right-hand corner there. Traffic jam for no good reason, right? No crash, no reduction in lanes, no construction, nothing like that. It's just human driving behavior. Human drivers are what we call string unstable. You know, someone in front of you brakes a little bit, you might brake a little bit more, and that causes what we call phantom jams to arise. At the bottom, this is a series of experiments that have been done that show that, hey, this is not just something that happens because of, you know, maybe the geometry or, you know, the glare on the road or something. If you do this, isolate pure car following behavior, you're going to see this. I've done this a bunch of times in a bunch of experiments several years ago. Without fail, you always see this. Okay, what I want to show next is I want to use this to motivate the rest of what I want to do. This is a video that I put together several years ago. If you've seen it, I'm sorry for showing it again. But basically what we did is we took one of those vehicles on that ring, we replaced it with an autonomous vehicle. We started, all the vehicles are human drivers. At the bottom, you see the speeds. And we go from that smooth flowing traffic to, you'll see pretty quickly here, a stop and go wave emerge. And then we turn on the autonomous vehicle controller. All the other vehicles, the other drivers have no idea what's going on. Like we asked them, we paid them to show up and just drive in a circle and didn't tell them what was happening. One vehicle is driving slightly differently. It changes the dynamics of the entire traffic flow. Now in this case, it does so for good. So what we can do is we can look at, engineers love these space-time diagrams up there. that's positioned the vehicle on the vertical axis, time on the horizontal axis. Each of those lines is a vehicle. When you see the line squiggle, that means there's a traffic wave. It's slowing down and then speeding up again. What we want is those unsquiggly lines, that smooth flowing traffic that we see, oh nice, right in the middle there, right? That's that smooth flowing traffic. And when we have all human-driven traffic, we see those stop and go waves. When we look at the speeds, we see that happen. One vehicle driving differently totally changes the flow of traffic. Okay, in this case, this autonomous vehicle is driving for good, right? It is improving the flow of traffic. In fact, what we see is a big reduction in braking events, unsurprising when you go from stop and go traffic to highly oscillatory traffic, or rather the other way around, you see a big reduction in braking events. We also saw a pretty big reduction in fuel consumption. We measured the fuel consumption of each vehicle with onboard sensors, and we see a pretty big reduction in fuel consumption. Okay, so that's what can happen if you design automated vehicles for good. I want to flip that and ask the opposite question. What happens if a small number of vehicles are compromised? And the compromise that I showed a minute ago here, the one at the top, where they took the vehicle, took over the vehicle and drove it off the side of the road, I'm going to argue that that is like an obvious attack. If that happens, if all vehicles of a certain make and model start driving off the road at a certain time, we're going to very quickly know not to drive that vehicle until we figured out what happened. That's an obvious attack. The more subtle attack that and I don't want to underplay this. This could be catastrophic. Like you could see a lot of crashes very quickly. I don't want to underplay that. But I think the one that's maybe a little more subtle is a certain number of vehicles are compromised, maybe through a malicious software update or something like that, to just drive a little bit worse. Not a lot worse, but a little bit worse. We've already seen how one vehicle changes its dynamics has the potential to totally change the flow dynamics. What happens if we do that the bad way, the other way, right? And so what I want to do today, the research that I'm doing here is sort of two parts. The first question is, okay, can that happen? How bad could that be? What would that look like? What are the impacts? And the second question is, can we do some sort of detection? Now, the challenge with the detection part, and you'll see the detection part is still very much a work in progress. The challenge with the detection part is that we don't know what the attack looks like. It's not like we're looking for specific driving behavior. There's a lot of people who are distracted drivers, maybe on their phone while they're driving and drive a little worse. So that's not exactly what we're looking for. Okay, so the one more point that I want to make before we really can dive into the research is there's all these different levels of automation. I'm sure you've seen some version of this plot, right? But you've got no automation, and it's sort of who's doing the driving, no automation, no one's doing the driving. But we have different levels of automation, sort of low-level automation, driver assistance, where some of the driving tasks are being handed over to the vehicle. Think of this as like adaptive cruise control or something like that. But most of the driving is still in the human driver. And as you go to higher and higher levels of automation, you take some of those driving tasks and hand them over, or more and more of those driving tasks, hand them over to the automated vehicle. In terms of the impacts on the flow generally, full automation, probably going to increase capacity, do some really nice things, as you saw a couple of minutes ago. Lower automation, it's still sort of an open question of what that will look like. But my point here is, regardless of the level of automation, there's potential attack surfaces on all of these vehicles. There's ways that all of these vehicles are looking at data of their surroundings, making some sort of driving decision, and if you feed them incorrect data, you might have driving behavior that is very different from what you might want, and that could have, from a traffic flow perspective, some pretty bad negative consequences. Okay, so how do we want to analyze this? The framework that I want to use is simple car following models. So these are ordinary differential equations that map the derivative of the acceleration of the speeds of the acceleration of a particular vehicle as a function of its surroundings. Specifically, we typically use the spacing, the relative speed with respect to the vehicle in front of it, and the speed of the vehicle itself. And so if we use this is a common framework that's used by traffic engineers and people who do traffic flow modeling all the time to model individual vehicle dynamics. And now we need to come up with a way to sort of define attacks. I'm going to look at two different types of attacks. I'm not going to look at communication-based attacks today. That's because that's still sort of very much work in progress. But we are also looking at communication-based attacks on this. But basically, it depends on where is that attack happening. So we're going to have a type 1 attack. This is some sort of malicious attack on the ACC control command. So ACC or fully automated. We have some sort of longitudinal control, and we're going to inject some garbage into that. And so we can write out what that looks like in terms of our updated ordinary differential equation. We basically insert some garbage. That garbage can be carefully planned or can be total noise. It's kind of a modeling choice. But either way, you're basically changing the command of how the AV wants to drive, and then you're changing that somehow to be a little different. The other way, you can imagine an attack that happens a little higher up. So you have a sensor. And instead of giving the true value to the vehicle controller, that sensor maliciously gives the wrong value to the controller, basically obscuring what the surroundings look like to the eyes of the vehicle. And we can also model that as in the ordinary differential equation or car following framework. So the first thing I want to do is just look at some impacts. What does this look like? I'm going to show those same space-time diagrams that I showed before. We've got a bunch of different vehicles. We've got green vehicles. Those are human-driven vehicles. We've got blue vehicles. Those are automated vehicles that have not been impacted. We've got red vehicles. Those are automated vehicles that have been impacted. And these are just basically different types of attacks or different intensities of attack. And as you can see relatively quickly, you just have a small number of vehicles. It's vast minority of the vehicles are automated, are automated and attacked. But even with just a handful of vehicles attacked, you start to get things that are dangerously close. In fact, if you look at things like time to collision, we see a big increase in, I'd probably say that a different way, a big increases in incidence of very small time to collision, and in fact, in some cases, negative. So in some cases, we start to introduce collisions without it being able to pinpoint who it actually was that caused the collision. Because it's not necessarily the compromised vehicle that's colliding. You've created traffic conditions that are conducive to collisions. Okay, we can also look at the traffic engineers love these fundamental diagrams, which basically show the speed density, or the flow density relationship rather. The smaller that diagram, the worse. And as you increase the severity of the attack, you start to reduce your capacity a little bit. So if you're a traffic engineer, you're not too happy about that. The other one is that false data injection attack. Again, we have a couple different parameters that we can vary over. Our baseline that I want you to compare to is this one this one right here, I believe, which has no attack. We see a little bit of human drivers have sort of naturally some waves arise, but this one right here. But as you increase the severity of the attack, you get to some pretty severe cases where you see, again, very unstable driving conditions where you might start to see collisions, even though those vehicles haven't been attacked in a way to necessarily create collisions. They're not the ones colliding, other vehicles are colliding. Again, we have a whole bunch of different, we can look at an ensemble of simulations at different densities. The story is basically the same. What you see is a general reduction in capacity. Okay, so that's the impacts part. I think from the impacts part, it's pretty clear that there's potential for severe adverse impacts when we look at these vehicles. You can see basically these types of attacks, even though they might be very difficult to identify, have the potential to change the way the traffic flows and therefore make it less efficient, probably increase fuel consumption, but definitely increase the number of times that you see sort of very low time to collision or even zero time to collision, so collision events. The next thing that I want to briefly talk about, this is that work in progress, is how do we detect these? And when it comes to detecting these, like I said before, you can't just say, is this vehicle, you can't just look for a specific template of bad driving. Because there's infinitely many ways that I can come up with of how I could manipulate the automated vehicle's behavior and to be worse than the default original driving behavior. And that's not, I can't just look for a specific thing. So instead what I have to look for is this normal traffic or is this not normal traffic? And does this traffic follow a distribution of what it might look like if it were normal, or does it follow a different distribution of traffic that might look like from an attack? So you might be asking yourself, why are there pictures of cats on this slide? And what I'm going to tell you is that those are actually not pictures of cats. But these are pictures of what a AI algorithm thinks cats ought to look like. And so the approach that we're taking is it's a pretty common approach in anomaly detection is these AI models, these generative AI models, are really good at learning distributions of what things ought to look like. So famously, they're used to generate fake cats. So it looks at a whole bunch of pictures. The internet has a lot of pictures of cats on it. Looks at a whole bunch of pictures of cats online and learns a distribution of what the pixels in a picture of a cat ought to look like. And then you sample from that distribution and you get these real looking cats, though if you look carefully, you'll notice that I think that one's missing a leg. And our idea is very similar. We want to look at a whole bunch of real traffic, which can be very messy. It can have a whole bunch of different things that occur that are not ideal, not smooth flowing, but there's some sort of pattern. There's some sort of order to that mess. We want to learn what that looks like. And the idea is then if we see something that's vastly different or that's somewhat different, can we identify that as a potential attack? I want to show some preliminary results of this. So we're using the same type of setup, this ring road setup. The reason we use this ring road setup is simply because it gives us infinite traffic. Every car has a car in front of it and a car behind it. And we look at different types of attacks, and we look at different types of normal traffic that might be quite ugly. The performance isn't perfect, but if you look at this column here, I'm looking at two different attack type scenarios, just like we had before. We're not identifying every single attack. Real traffic is very messy, but 75 to 85% of the time, we are able to identify whether or not there was an attack. Okay, so in summary, automated vehicles have a lot of vulnerabilities to cyber attacks. I'm only talking about like a very, very small slice of that. I think all of the talks today have also only really covered a small slice of that. There's a lot of potential attack surfaces. The way that I like to look at this is sort of thinking about it from a traffic flow perspective, where we know changing the dynamics of a small number of vehicles changes the dynamics of the flow. This can be good or bad. In the case of sort of a stealthy attack, this might be leveraged for bad, right? It may decrease capacity, increase crash risk. However, there's potential for using some of these anomaly detection techniques, applying them to this context to be able to identify whether or not the traffic is compromised. I want to apologize. I tried to get you out to your coffee break on time, and I did not deliver on that. I am 1 minute over, but thank you very much for your attention. And I'm happy to answer any questions over coffee.